Hello students, I welcome all of you to this novel initiative of Department of Higher Education, Government of Madhya Pradesh in developing e-content for postgraduate classes. We are today going to study the third semester M.Sc Physics, second paper. The title of the paper being Nuclear and Particle Physics, and specifically I would be talking about the Meson theory of nuclear forces. Myself, Dr. Seema Hardikar, I am working as Professor Physics in Sarojini Naidu Government Girls Autonomous College, Bhopal. As I already told you, we will be dealing with M.Sc. 3rd Sem Physics Paper 2, which is about nuclear and particle physics, in which we'll be studying Unit 1, which deals with nuclear interaction and nuclear forces. And specifically, I would be talking about these nuclear forces and the Yukawa theory related to nuclear forces. Now, before proceeding on with the module and lecture, I would like to tell you that it requires a basic knowledge about classical and quantum electrodynamics. Of course, you should know the properties of the nucleus because it is the nuclear forces that you are going to study. And I don't think so. I need to say that since you are talking on a quantum scale, you should have a brief idea about quantum mechanics also. After finishing this lecture, you will understand the basic nature of nuclear forces, and so also you would understand the exchange character of nuclear forces, specifically knowing the nature of pion. Now students, what is a nuclear force? Yes, we all know. Nucleus consists of protons and neutrons, and since the protons carry a positive charge, the electrostatic force of repulsion between them should cause the disruption of the nucleus. The gravitational force between the nucleons is too weak to account for the observed binding energy of the nucleus. It means that there should be some other force that binds the nucleons together, and we call this other force as the nuclear force. Let us consider the charged particles to be protons. Yes, we know that protons are positively charged particles, so definitely they will be repelling each other if you talk in terms of electrostatic forces. And the magnitude of the force between these two charged protons would be given by 1 upon 4 pi epsilon 0 q1 q2 upon r square. If you calculate the value of this, taking the charge of proton as 1.6 into 10 to the power minus 19 coulomb, and the distance between the two protons of the order of 10 to the power minus 15 meters. Students, do you want to consider why we have taken the distance between the protons to be 10 to the power minus 15 meters? The reason is that we all know the diameter of the nucleus is of the order of femtometers, which you also call as Fermi. So when we calculate this force, you get the value as 230 newtons. Can you imagine the magnitude of force that is acting between these two protons? In spite of this, subatomic particles are able to stay in the vicinity, what does it mean? That there is some other force that is holding them together, and you call it as the nuclear force, which is considered to be a lot more stronger than the Coulomb's force of repulsion. We are very well aware of the three well-established particle interactions: the electrostatic interaction, the magnetic interaction, and the gravitational interaction. The electrostatic interaction is basically governed by the inverse square law of distance between the charged particles. And yes, it is a long-range force. You just saw in the previous slide. If you talk about the magnetic interaction, it is given by mu naught upon 4 pi m1 m2 upon r square, where m1 m2 are nothing but the pole strengths and r is the distance between the poles, and mu naught upon 4 pi we all might be remembering has a value of 10 to the power minus 7. You can calculate this force. Talking about the gravitational interaction, it is again governed by inverse square law of distance, which is a long-range force and acts between masses of two bodies. So we all know in this universe, the celestial bodies all are governed by gravitational interaction. Now this is a table which gives us a comprehensive idea about the different types of interactions, their relative strengths, the range to which these interactions act, and also about the exchanged quanta. Now, when I talk about the Yukawa theory or the Meson theory of nuclear forces, to be more specific, I would later tell you why this Meson theory of nuclear forces is also called as the Yukawa theory of nuclear forces. What I'm more interested in is the exchanged quanta. As I already told you, it is this exchange character of the nuclear forces which is of prime importance. What do we see in this table? The gravitational forces are the weakest of all forces. Can you imagine? Yes, it is beyond our imagination. Why? Because what do we see in the universe? The earth moving around the sun, and the moon moving around the earth, and the sun moving around the in the Milky Way galaxy. So all these things, do they ever suggest that gravitational forces are the weakest of all forces? And what is the exchanged quanta in terms of gravitational forces? You call it as a graviton, having a zero rest mass and spin 2. I have drawn this table in a typical hierarchy manner. After gravitational forces, you have what you call as the weak nuclear forces. These forces are 10 raised to the power 25 times stronger than the gravitational forces and act at a subatomic scale, meaning thereby 10 to the power minus 18 meters. And in this, the exchanged quanta are W and Z bosons. Talking about the electromagnetic forces, they are 10 raised to the power 36 times stronger than the gravitational forces, are of long range, and the exchanged quanta is virtual photon. In case of strong forces, which you term as the nuclear forces, are 10 raised to the power 38 times stronger than the gravitational forces and act in subnucleic range. And this range is the diameter of the nucleus, which you suggest as 10 to the power minus 15 meters. And the exchanged quanta here is a pion. And we will be calculating the rest mass of this pion. Just wait. Now, how is the nuclear interaction different from above three interactions? It's strange, of intriguing nature, and has been the most challenging problem in physics. In 1953, Bethe said it has consumed more man-hours than given to any other problem in physics in the history of mankind. And unfortunately, students, there is still no well-established law for this nuclear forces. बच्चों, what are these nuclear forces? इनकी क्या प्रॉपर्टीज हैं? बहुत शॉर्ट में हमको इनकी प्रॉपर्टीज जानना होंगी अगर हम न्यूक्लियर फोर्सेस की थ्योरी को पढ़ना चाहते हैं। हम सबसे पहले कहते हैं कि ये शॉर्ट रेंज फोर्सेस होते हैं। ऑब्वियस सी बात है, अगर इनको न्यूक्लियॉन्स के बीच में एक्ट करना है तो वो न्यूक्लियस के अंदर ही तो एक्ट करेंगे। तो न्यूक्लियस के अंदर यानी 10⁻⁻15 मीटर्स फेम्टोमीटर्स की रेंज में इन्हें एक्ट करना है। मतलब हमारा कहने का क्या है कि एवरी न्यूक्लियॉन इंटरैक्ट्स only with those nucleons which are in the immediate vicinity of that nucleon. The second property is they are charge independent. What do you mean by charge independent? Well, that is understood in a fact that since they are acting also between neutrons and neutrons do not have any charge, so they need to be charge independent. Is it true or not? But other than that, there are experimentally verified facts also proving that nuclear forces are charge independent. One of those experiments or the experimental fact is about the mirror nuclei. What are mirror nuclei? These mirror nuclei are those nuclei in which the number of nucleons remains the same, but the number of protons and neutrons are interchanged. And surprisingly, it has been proved that the magnitude of proton-neutron, neutron-neutron and proton-proton charges has always been found to be the same. Moreover, the binding energy of a particular nucleus also does not depend upon the number of protons and neutrons in the nucleus, but it only depends upon the total number of nucleons in that particular nucleus. As we have already seen in the table before, they are the strongest known forces in nature. Mind you, these forces are spin dependent, meaning thereby that the strength, the attractive strength of these nuclear forces is totally spin dependent. Those with parallel spins, the strength is more as compared to the nuclear force acting between two nucleons having spins antiparallel. Another important property is the property of saturation. What does it mean that nuclear forces are saturated? What do you mean by that? You mean to say that they interact only with nucleons in their immediate vicinity. It is not that every nucleon interacting with every other nucleon inside the nucleus. No, it does not happen like that. A nucleon interacts only with its immediate neighbors. Nuclear forces are non-central forces. What do you mean by that? Non-central character means that the line of action of these forces is not along the line joining the two nucleons. This is the first point. The second point is that this nuclear force also does not depend upon the distance between those two nucleons in between which it is interacting, but it depends on the spin and the relative orientation of the two nuclei that are being considered. And the last but not the least is the exchange character. And it is this character that today's lecture is dealing with. What does it say? That nuclear forces can be appreciated only and only if we consider that there is an exchange of particles that is taking place. Now look at this. Do we remember the Coulomb's law? Yes, we do. But what happens? In terms of classical electrodynamics, if you talk, there is no direct interaction between the two charges. Instead, a classical field is created around each charge And remember, classical electrodynamics says that the field is continuous. And the interaction takes place through this field. That means the field becomes the mediator. And if you move on to quantum electrodynamics, the only difference is that the field is not continuous, but it is quantized. And we say that the exchange of virtual photons takes place. And these photons are not experimentally observable and exist for a very short period of time. Now, this is just a potential energy graph which you have been drawing since your undergraduate classes. What does it suggest? That Fr is equal to minus du by dr. Yes, I know you know this formula so well. That means it is the negative of the slope of potential energy curve. What do you see over here? At distances less than 0.8 femtometers, these nuclear forces are repulsive in nature. Distances between 0.8 and 2 femtometers, they are attractive. And beyond 2 femtometers, they are negligible. Now, how are you going to understand this? It's very easy. See, less than 0.8 femtometers, they have to be repulsive. Because if they are not repulsive, then your nucleus would collapse. Right? Between 0.8 and 2 femtometers, they have to be attractive, otherwise the nucleus would disrupt. And beyond 2 femtometers, of course, they become negligible. So what is a nuclear force? Yukawa in 1935 gave his Meson theory of nuclear forces, in which he said that the nuclear force exists as a result of exchange of particles. In other words, neutrons and protons are continuously emitting or absorbing another particle in between them, and the exchange of this particle is creating the effect of force which is holding both of them together. And unlike photons, this particle does have a charge and rest mass. Now, who was Yukawa? He was born on 23rd January 1907 in Tokyo. He graduated in 29 and published his theory of mesons in the year 1935, for which he received Nobel Prize in 1949. He went on to become the first chairman of Yukawa Institute of Theoretical Physics in the year 1953. A very well-known scientist of nuclear physics. Now you can understand this Meson theory of nuclear forces with a very simple analogy. And yes, let me remind you why I was calling this Meson theory of nuclear forces as Yukawa theory of nuclear forces. Students, अगर हमको एग्जाम में कोई Meson theory of nuclear forces न पूछ करके Yukawa theory of nuclear forces पूछता है, तो it is one and the same thing. Now let us understand this analogy. क्या दिख रहा है चित्र में? दो बच्चे बॉल के साथ खेल रहे हैं और बॉल को कैच कर रहे हैं. एक बच्चा फेंक रहा है, दूसरा कैच कर रहा है, दूसरा फेंकता है तो पहला कैच करता है. When A throws the ball at B, A experiences recoil, and since B has to catch the ball, obviously it has to move a bit forward. Both A and B have to move forward and backward so as to not drop the ball. Ball अब गिराना नहीं है उनको. It means that while throwing at each other, they would move backward, or we can say they would experience a repulsive force, and while catching, they would move forward, or we can say that they are experiencing an attractive force. Another most important thing over here that you need to remember is that they will neither go too far away from each other nor would come too close to each other just to avoid the dropping of the ball. And I hope you are clicked to the diagram which we had drawn less than 0.8 femtometers and between 0.8 and 2 femtometers and beyond 2 femtometers. I hope you are able to correlate the two. So what do you say? You say that they maintain an intermediate distance so that they are connected by some kind of a bond which is holding them together and not allowing them to either go too far or too close. It's very important. Now, if we believe in Yukawa's theory and if we consider that there is an exchange of particle that is taking place, that is if it is being emitted from a proton, then the mass of proton should reduce by that amount. That means if I hold the equation that is written there on the slide being true, where a proton is getting converted into a neutron with the emission of a pi plus meson, then the mass of the proton should reduce by an amount mp minus m pi plus. That is, if any nucleon is either emitting or absorbing a pion, then its mass should change. Either it should increase or decrease. However, experimentally, the mass of nucleons are not found to be fluctuating over time. And this is very, very surprising. You all have studied conservation of mass and energy. How is it possible? Right? So that we have to understand in the coming slide. And the explanation can be given on the basis of Heisenberg's uncertainty principle, saying that it can be true only and only if the transfer of energy takes place for a very short interval of time, because a quantum state existing for a short time cannot have a definite value of energy. This is Heisenberg's uncertainty principle. That the product of uncertainties in determining the energy and the time is always greater than or equal to h cross upon 2. If we consider the distance between two nucleons as 1.4 Fermi, there is nothing new. I know it has to be in this order. Then the velocity with which the particle moves, if you consider it as the velocity of light, you have delta E as being written as mc square. So m pi plus multiplied by c square multiplied by delta t. What would be delta t? It would be the distance upon velocity. So what is the distance that you have taken? 1.4 into 10 to the power minus 15 meters. Divided by c, which is the velocity of light, which is 3 into 10 raised to the power 8 meter per second, should be greater than or equal to h cross upon 2. And when you solve this equation, you get the value of m pi plus as approximately equal to 0.25 into 10 to the power minus 27 kilograms. And considering the rest mass of the electron to be 9.1 into 10 to the power minus 31 kilogram, you see that the mass of pi meson comes out to be 270 times the rest mass of the electron. Of course, in 1947, Powell discovered these pi mesons of the same mass in cosmic radiations. Now here I have drawn a small table depicting different pi mesons, the charges associated with them, their rest mass energies, their rest masses, their spin and their magnetic moment. Of which I would say everything is important. But for the coming discussion, if you ask me, I would say the spin of pion is very, very important. Let us move forward. This is the different interactions between the pions that I have presented. You can just go through it. Now, coming the most important part of this Meson theory of nuclear forces. According to Yukawa's hypothesis, yes, we have studied up till now, that nucleon is regarded as a source of field quanta and hence of the Meson field in a manner similar as the charge is regarded as a source of photon field. A nucleon can be thought to be surrounded by virtual pions. The meson field possesses a certain type of interaction which can be represented by a potential function, and what I want to do today is to find out the expression of the potential function with a simple derivation. Let us see how it is to be done. To interpret the nucleon-nucleon forces, comparison of Meson theory with quantum theory of electromagnetic interaction should be done. To obtain a pion wave equation, we express the total energy E of a pion in terms of pion rest mass energy and momentum by the formula. It is very well known to all of us. We have been studying it since relativistic mechanics. We have studied it is E square is equal to P square C square plus M square C to the power 4. And since I am talking about the pion, I have replaced this M by M pi. Now, as I told you in that table, you have to know that these mesons are zero spin particles. So the mathematics that we'll be doing over here, where we will be considering the Klein-Gordon equation, because it is used in quantum field theory for explaining the field of zero spin particles, and hence it is used for description of pi mesons. It is, of course, the quantized version of the energy momentum relation E square is equal to P square C square plus M square C to the power 4. Now let us move on to the derivation. What does Klein-Gordon equation say? Minus 1 upon C square del square psi by del T square plus del square psi is equal to M pi square C square upon H cross square psi. What is psi? It is the wave function associated with the particle. M pi is the mass of the particle, right? C, of course, is the velocity of light. All these things you have already studied in quantum mechanics. This is just a revision. But yes, of course, we will be dealing with this equation to understand the Meson theory of nuclear forces. According to Yukawa, the radial part of this equation should give us a potential for the relativistic particle. In addition, Yukawa also assumed the steady state process and introduced a pion wave function phi r instead of psi rt. In the above equation which you are seeing on your screen just now, which I have named as equation 1, the wave function psi is a function of r and t both. But what Yukawa did is that he assumed a steady state process, that means no time dependence, and introduced a pion wave function phi r, a scalar wave function, in a manner that psi of rt should be replaced by phi of r, and you get the radial part of the equation as del square phi minus m pi square c square upon h cross square phi is equal to 0. I'll give you a second just to view this very carefully. I hope you are able to substitute instead of psi rt, phi r in equation 1. And what do you get? Let us move on to the next slide. Del square phi minus m pi square c square upon h cross square phi is equal to 0. I hope you understand mathematics to the level that the same equation can be written as 1 upon r square del by del r of r square del phi by del r minus m pi square c square upon h cross square phi is equal to 0. Students, I know you might be smiling just because that I am explaining it in such a simple manner. This you have already studied very nicely in your lectures of quantum mechanics. Let us move forward. Let phi of r be equal to v. Then replacing phi of r in the earlier equation, we would get 1 upon r square del by del r of r square del v by del r. It was earlier del phi by del r. So now we are writing it as del v by del r minus m pi square c square upon h cross square v is equal to 0. Differentiate it and you get del square v by del r square plus 2 upon r del v by del r minus m pi square c square upon h cross square v is equal to 0. Just take 2 seconds. Just take 2 seconds and see whether you are able to differentiate it or not. It is simple mathematics of your school standard. Let us move forward. Now, what did Yukawa assume? He assumed that let me take another function u, which is rv. And what did he assume? That u is a function of potential v, and v, of course, in turn is a function of r. So if you differentiate u is equal to rv, you will get du by dr is equal to r dv by dr plus v. And the second differentiation of the same equation would give you d square u by dr square is equal to r d square v by dr square plus 2 dv by dr. Name it as equation 3. And substitute this value of d square u by dr square from equation 3 into equation 2 that was there on the previous slide. You will get d square u by dr square minus m pi square c square upon h cross square u is equal to 0. Let us move forward. The general solution of this equation. Yes, I know. You remember the general solutions that we have studied in differential calculus. It can be given as u is equal to u naught exponential plus minus m pi into c upon h cross r. And since you had already taken u is equal to v into r, so you can write the same equation in terms of v, which will be u naught upon r exponential plus minus m pi c upon h cross into r, and name this equation as equation 5. Now what this equation 5 is representing is the effective potential between the two nucleons. Very important. This is what we tried to derive. Yukawa qualitatively used this equation by introducing a coupling constant g square for u naught, and he obtained something like v is equal to g square upon r exponential plus minus m pi upon h cross c r. You see, important is the exponential function that you are getting over here. This is a strong force which is of short range and always attractive in nature. So Yukawa considered the solution in the form of v is equal to minus g square upon r exponential minus m pi into c upon h cross into r, and replacing h cross upon m pi into c by capital R, he got the expression v is equal to minus g square upon r exponential minus r upon r. And he named this equation 6. Let us move forward. Comparing this equation with relation for Coulomb potential, what do you see? That the nuclear potential decreases more rapidly with distance from the source than the Coulomb potential by exponential factor. If you want to understand what the Coulomb potential would be, it is very simple. You get the value Vr is equal to minus g square upon r, which gives you the inverse relationship with r. Right? Moving forward. The first derivative of 6 is positive, meaning that the strong force is always attractive. And here the capital R, which we had replaced, is called reduced Compton wavelength of the particle. And using this ratio and considering the effective range of strong force as 1.5 Fermi, Yukawa calculated the mass equivalent energy of Yukawa field as equal to 125 MeV. And then the search began. During 1940, physicists started looking for particles with mass equivalent energy of 125 MeV. And in 1937, muon was discovered in cosmic rays. Initially, it was assumed to be a Yukawa meson. In the year 1946, pion was discovered in cosmic rays having the mass energy in the range 135 to 140 MeV. Later, it was also verified that conversion of pion to muon is possible, and this plays a very important role in explaining the low energy property of strong nuclear forces. I hope this was a self-explanatory mathematical derivation which made you understand the physical nature of the Meson theory of nuclear forces. For further reading, I would like you to please refer to Nuclear Physics by D.C. Tayal. You can also refer to Fundamentals of Nuclear Physics by Jahan Singh and also Nuclear Physics by S.N. Ghoshal. Now the time has come to assess yourself. Which of the following is true? It's very interesting, mind you. There are certain things which I have put in this example of which I have not talked directly in my lecture. The very first thing is, the very first option is nuclear forces are strong forces. Yes, you don't need to tell me, right? Neutron has a negative magnetic moment. Now this is very important. See, very interesting. Neutron has a negative magnetic moment because for a fraction of its lifetime, it is dissociated into a proton and a negative pion. Very, very, very important. If you remember the slide where I had given you different type of nuclear interactions, it was there. The third thing, pions are virtual particles, each consisting of a quark and an antiquark. Yes, it is true. Yes, it is true. And the last option, none of the above is true, is not true. So the answer is A, B, and C are all true. Moving on to the next question. Moving on to the next question. Find the range of nuclear force mediated by a meson having mass corresponding to 550 MeV. Are you understanding the problem? I want you to find the range of nuclear force mediated by a meson. And I've given you the mass of that meson. So what would be the value of delta E over here? Remember the Heisenberg's uncertainty principle which we had, established in the slide just some time before? It was delta E into delta T should be greater than or equal to h cross upon 2. Now what is the value of delta E? It is 550 multiplied by 1.6 into 10 to the power minus 13 joules. I know you know how to convert MeV into joules. So what do you get the value of delta T? It comes out to be h cross upon 2 delta E. And once you get the value of delta T, I know finding out the range would not be much difficult because range would be nothing but C delta T, right? Because velocity is displacement upon time, we all know that. So range is C delta T and you get the value equal to 0.36 Fermi. I thank you all from the bottom of my heart for listening to this lecture so nicely and so carefully. Would definitely want to meet you in future lectures. Thank you so much.